Hey guys, and welcome to another session in the Mind Grid. And today we are again looking at MyHDL, and we're going to take another example to see how MyHDL can improve our modeling for FPGAs and ASICs, and it can lead to you doing some work without the need for expensive tools. If you are a freelancer, it can help you get started without all the licenses that are normally needed to do complex hardware design. So without ado, let's look at it. So what is MyHDL? The short description is MyHDL is a free open source package using Python as a hardware description language and verification language. Now, this is useful for a variety of things. Modeling, which is, you can make high-level RTL modules using Python. And Python is an elegant language as it's written here, but it can be used to do complex modeling. And Python is outstanding for rapid application development and experimentation because it's so simple to use and learn. And most of us know how to use Python, especially ChatGPT and other LLMs are also very good at Python. So that is probably the first place where you can get some help if you need it to do MyHDL. Also, my experience has been that a lot of initial work in MyHDL can very easily be done using ChatGPT because it is extremely good at writing the HDL code, which I normally don't do for Verilog or VHDL. Now, hardware modules are modeled as functions that returns generators. So this you will see, this specific thing you will see when we show an example that all the functions return generators. Now, I'm not quite familiar with this concept, but you'll see that the functions return these generators, and these are used by the Python backend that MyHDL has to create all the simulation and ability to execute the RTM. So MyHDL provides classes that implement traditional hardware description concepts. That's very important. And you will see that as we show you instantiation of a small FIFO today. And it provides signal class to support communications between generators, class to support bit-oriented operations, and class for enumeration type. So all these are already provided as a starter. So it's good enough to do fairly complex modeling of hardware logic. And it provides simulation verification. So the built-in simulator runs on top of Python interpreter. It supports waveform viewing using the VCD files and GTK wave and whatever else tools if you have some. With MyHDL, Python unit test framework can be used on hardware designs. Although unit test is a popular modern software verification technique, it is uncommon in hardware design world. So in most cases, we end up writing comprehensive system level test benches and so on and so forth, which is also possible here. Conversion to Verilog and VHDL, that's also possible. MyHDL can be converted to Verilog or VHDL. This provides a path into traditional design flow, including synthesis and implementation. However, convertible subsets is much wider than the standard synthesis subset and includes features that can be used for higher level modeling and test bench modeling. Obviously, there's more stuff than RTL, and that's normally the case with Verilog VHDL as well, right? So it's worth looking into that. And I think last video I also covered installation, but if you look at it, it's fairly simple. It's just a pip module in Python, and you can just say pip install MyHDL or pip install upgrade MyHDL. You get the latest, and that is all that there is to it. It's a fairly simple installation. Takes you just a minute to do that. And then why MyHDL? So one of the things that you'll find here is it's open source and it's completely free, right? That's so important because most of the tools that are available in RTL design, especially bigger designs, it's not going to be free. There's always like limitations to, what you can get if you are designing Verilog, system Verilog. There is support issues. There is all kinds of issues. So this is excellent resource because you can build your FPGA or ASIC designs or test them without the need for any expensive tools. This is completely free. And you're building it from scratch, so probably it's not going to be compatibility issues either, because really we are building from scratch, and it's not like we are importing a bunch of code that pre-existed and IPs and so on. Now the downside is that it's the same thing, that you're missing all the IPs that normally would be available to you, and you have to create them here, right? But if you're really designing your code, you should be able to test your IP and maybe model the remainder of the IPs as more simplistic IPs, and therefore you can test your main ideas and get a head start, right? If you're new to hardware digital design, let's be honest, there's a lot to learn, and it'll be a lot of hard work. However, choosing the right development language makes it easy, and Python is one of the easiest languages to learn. So that is one of the key advantages of MyHDL, is because it is using Python, which is fairly easy. Dynamic language power. So if you're practicing hardware designer, you're probably using dynamic languages, sometimes called scripting languages, in your workflow already. For example, Tcl is popular, and designers use Perl to glue things together. Others use Ruby or Python for the purpose. It's clear that these active dynamic languages play essential role in modern digital design. Verilog VHDL is not enough. Many designers even prefer languages over HDL, right? Because they use it so much to control all the other stuff. Wouldn't be great if one could use such a language directly to design hardware? Absolutely, why not? Right? I love that idea. The fact that you can use one of these languages that are so much more flexible to do RTL design, that has been the missing part all this while, right? And so this is fantastic idea. Whoever came up with this is an amazing idea, and I totally love it. Modern software techniques. So in software methodology world, a lot of innovations going on with buzzwords such as agile, rapid, scrum, blah, blah, blah. And this is not just a hype. And new ideas and techniques offer real improvements over the development process. Naturally, there emerging community of modern software languages such as Python. So all those things are available in Python much sooner than they would be made available in an actual FPGA language like Verilog or VHDL. HDL-based design has many similarities with software. New ideas are potentially quite relevant. Nevertheless, the hardware design world seems detached from them. So there you go. That's, again, another key word, that the hardware world doesn't seem to catch on to all the new software things, but being in Python, you might be able to get those. So so that is a reason, a motivation for doing that. Now, the next one is algorithms and implementation. Unified Python's ideal language for algorithm development, and many engineers use it for this purpose. Commonly, this work and subsequent HDL implementations are done by different engineers. They use a different set of tools that require specialized level of knowledge. MyHDL, a big step towards unification of two domains. MyHDL, an algorithm or model designer can explore HDL implementations. An HDL designer can explore algorithm model design, all within the same environment. Of course, the conversion from algorithm to HDL implementation still requires knowledge of HDL design. Being able to do this while staying in the powerful Python environment can be a significant boost. So both algorithm and implementation are happening all at the same time, and you can leverage power of Python to do either, right? So that is great. You can target both Verilog and VHDL when you convert them. Explicit but not verbose. So VHDL has many virtues, but conciseness is not one of them. Many feel that syntax is verbose and even redundant, and many experts need a manual nearby to get the syntax right. That's absolutely correct. It's too heavy, and Python is different. It's concise. One of the reasons it is dynamic language without declarations. but the major reason is its well thought out design. Moreover, it achieves this without resorting to magic. The code remains explicit, but the syntax has been reduced to the essence. So that is another good reason. And then there are some more ones. So it does have signals and variables like VHDL, signal assignments. Let's look at this one. Signal assignments are important, fairly important. So in this one, signal assignments are not natively present in software languages. So normal part of processing, we can see this sort of assignment happens in Verilog, VHDL world. And that is not something that software people actually completely understand, right? This blocking, non-blocking stuff that hardware designers are used to. Even when this code is inside procedural code, the semantics are concurrent, and in particular, the value of a used on the second line is not the one assigned. Yes, absolutely. And that is fairly important. The FPGA designers understand that these non-blocking assignments, how they operate. MyHDL uses a different approach. Instead of special assignment symbols, it uses attributes, right? So instead of doing this special symbol for equal, it just uses this. So this means that A.next is B, right? And it's not A that is getting assigned. This is kind of a little bit hard for software people to understand, but this is obvious, right? This is absolutely clear. You're using the same equals, but we are just saying A.next, and behind the scenes, this is just an attribute of A, because A is a signal, it's the attribute, and so the simulator obviously will convert this. At the clock cycle, it'll take, A will be assigned B at the end of the clock cycle. So this is the approach that MyHDL has taken. Straightforward integer arithmetic. When writing synthesizable VHDL code, you typically use the signed and unsigned types of arithmetic operations. These are representational types that focus on bit representation, bit width. Yes, and the operators defined for such have stringent requirements on types and bit widths and operation results. As a result, you'll typically need a lot of conversion functions and resizing. Many designers take this for granted and view it as a result of VHDL's strong typing. In reality, it's a consequence of using low-level types. MyHDL follows a different path, but one that has actually been shown by VHDL in the first place. It has been the INT-BV and type, which is an integer-like type whose values can be constrained like in VHDL. However, unlike VHDL, there are no artificial limits on minimum and maximum values it can take. Moreover, and again, unlike VHDL, the type has indexing and slicing interface to access representations. So you will see this, we will use this int-bv quite a lot. The result is that the synthesizable MyHDL, you can basically do arithmetic using integers. Therefore, all issues with signed, unsigned representation simply disappear. The converter to VHDL infers the required conversion and resizing automatically, thereby automating a cumbersome task. Signed arithmetic that works. So signed arithmetic in Verilog can be quite confusing. The reason is that you mix signed and unsigned operands. The operation is done in unsigned mode. This is the opposite of what should be done to get normally expected results. To avoid this, operand should be explicitly cast to signed. In MyHDL, these issues do not exist because you can basically use integers for arithmetic. Using the int-bv type presented in the previous section, the converter to Verilog infers the required cast and bit extensions, the bit extensions automatically. When you do the signed arithmetic, all the extensions, everything happens automatically. So if you just stay with the integer operation, everything happens till you convert, and the conversion is done by the conversion part. So everything just, the arithmetic works out much better than Verilog and VHDL. So that is it, guys. So now we're going to jump to the the demo part again in this time, and we are going to look at something we call SC FIFO, which is a single clock FIFO. Okay, let me see if I can make this slightly bigger. No, okay, let's just stay with that. So in this, you can see that MyHDL is actually the software library, and from there we import a bunch of things. Delay, instance, block, always, always come. Into PV, these are our signals and signal definitions and types, and then some of the test bench stuff. So this is not just a C5 at the bottom of it. We'll have some little bit of test bench. So there you have it. That's all that we need. And add block again. Add block is equivalent of a module, and so SC5 was a module. Now Python doesn't have this equivalent concept of parameters and generics. So we're just going to stick in width and depth here, right there. And then when you define all these things, clock, reset, write enable, read enable, data in, data out, full empty, fill level, and all that. Now, the key thing to note is that most of these signal definitions don't, in fact, all of these signal definitions will come from a level above, right? Wherever the test bench, it'll define what the data in is, data out is. So essentially, this is agnostic. But if you're using these widths inside the module, you need to be told. So you can convert them as a generic here. This is all it takes. It's just an input, and it'll become a generic, because let's look at this. So the depth can be converted into a parameter here. You just define another signal. And then same way the FIFO memory is defined. So FIFO memory is a signal with a certain, it's a bit vector, and initial value is 0, and the width, this is the width of each element, right? So width is whatever bit, let's say it's 8-bit data path coming in, so width is that, and for blah underscore in range depth, so it creates those many elements. And so FIFO mem is really a list, right? Is a list of this data type in PV, and with a width of whatever comes in. Right pointer, again, based on what we calculated from the parameter depth, is the depth parameter. So it gives you right pointer, read pointer, and FIFO counter. So that's all we got. And then in the next section, we have this always on positive edge of clock. This is the write logic. So if reset, FIFO count goes to 0. If write enable and not read enable and not full, which means that we are letting the write through, then FIFO count increases. If we are reading and not writing, and we are not empty, then we decrement it, right? And if you're both reading and writing, then obviously the FIFO count stays at 0. Sorry, it remains at the same value. So that is there. And then when we do the logic for write operation, the same thing, positive edge of clock at always, and then you define this logic, and then if reset write pointer is 0, if write enable and not full, then the memory is written, whatever the write pointer is, and then you see this concept of dot next. So that means that it's like the non-blocking assignment, and data in is taken here, and then write pointer will change to write pointer +1. That's all good, right? So that is the write pointer manipulation. Same way the read logic would do the if reset read pointer goes to 0. If read enable not empty, then the memory is read out at the read pointer, and read pointer is incremented. And then the full, finally, this is the combo logic output. So you always have the equivalent of the combo logic here is always comb, and here's where you would provide the other logic. So full dot next is equal to FIFO count equals depth, empty equals FIFO count equals 0, and fill level next is FIFO count. So FIFO count was just how many elements are there. So empty and full are thus done, and if you're full, you're now going to go ahead and write more. It's going to stop when the FIFO count reaches depth. So there you have it. That's the, and oh, by the way, so now most important was we said generators, right? So you look at this. So the return of this is all the all the sections that were annotated, so count logic, all the always blocks, and if you have any instances, all the instances have to be returned here as well. It's very important to return everything. This is how this MyHDL works, is that you have to return all the key blocks and instances, right? Anything that's and decorators have been used, like always, comb, always, etc. They all have to be returned here for it to work. Now the next stuff is that we have another module, which is the TB and FIFO TB. We, again, like I said, here we have instantiated this as C FIFO, but you have to define all the signals. So signal is the class that contains these definitions of all the the signals as we are used to in like Verilog and MYHDL. Now here, so clock and reset are just Boolean signals, and they're initialized to some value. And the reset is actually active high. As you can see, the default value is 1. This is not the width, right? Boolean is just a single bit, obviously, and these are just the default values. Then write enable, read enable are also Booleans, and then data in, data out obviously are 8-bit vectors. Now keep in mind, this really means 7 down to 0, because the first one's, even though it's written as 8, it really means 7 down to 0. It's not inclusive. Full and empty are Booleans with a default value of 0. Fill levels, another 4-bit vector, and that's how you define it. And then we instantiate the FIFO that we have designed above. Width is 8, depth is 16, and then all the signals that we have defined above. That's how you instantiate the FIFO. And then the always block that generates a clock. So you use delay 5 here like this. So it's a 10 nanosecond clock. We invert the clock every time it changes, and then we delay 5 and generate. So it's very similar to Verilog in a way. Then finally, stimulus. So stimulus block uses add instance. This is like the equivalent of initial block at instance, right? And stimulus just goes ahead, reset. Reset next is equal to 0. And so reset's taken away. Notice that reset's taken away right at the beginning. And by the way, this was generated by ChatGPT, so you can see that ChatGPT is extremely good. I've made some tweaks to it, but ChatGPT pretty much generated the SC FIFO. That was kind of a working FIFO. If I missed something, let me know in the comments, but in general, ChatGPT is pretty good. Test writing the FIFO, when you write to it, it's just generating in a for loop data, write enable, read enable, and basically this is equivalent of add clock, add positive edge of clock. So yield, and then when the positive edge comes, you move on. So you write 5 words into the FIFO, then you try to read 3 words from the FIFO, and so you do those, and then you do a reset, and then you do a reset, and then you stop the simulation. And obviously in this block also you have to do the same thing. You have to return all the generators, which is all the decorators that you had inside your block, right? And then finally you will go ahead and do a test bench. So you will instantiate even at the top level the FIFO TB, and then you have to do this for enabling the VCD trace, and then run it. So now let's run this. So we're just gonna like run Python 3 and scfifo.py, and you'll see that it'll run. So it's done the writes. So you can see here they've done all the writes, all the 5 writes. They've done all the reads, so it was all okay. Empty is false here, and then on the right side there's no full levels. I mean, because we go all the way to 15, so it's not really full. So full is false, and then we actually do a reset. Now I can pull up GTK wave and FIFO tv.vcd, and if I pull up the waveform, I can show you that you can actually, there's something inside it as well. So there's FIFO memory. Wow. So you can also see the FIFO memory. That's very interesting. So now I can just inject all these here, and if I maximize this, you can see that all the waveform is present just like any other simulator. The waveforms, guys, are present exactly as you would need them. And so this is fantastic. It's all there with just very few lines of code. All the waveforms are there for you, and you can see that the writes are happening. So empty is going away as soon as you write, and the writes are happening. You did 5 writes in the beginning, which is all there. And now notice, guys, that all the signals were initialized even without a reset, so we didn't really need a reset here. But normally when you're designing RTL, you should have a reset. You should provide reset in the beginning because that's how we design. So this is the part that I think ChatGPT missed. We should have done maybe several clock cycles worth of reset right up front, and that is something I would have done. Then there's obviously the writes happening in the beginning. You can see that write enable goes on high, and then after write enable goes down, the read enable will go on. So we will start reading, but the point is that at this point, because the reset has been performed here, all the pointers have gone to 0. So the device is empty here. And if you try to do a read, right? So if you do a read enable high here, read enable high, when you're trying to read, it just ignores, it doesn't read anything. So the pointers, if you look at the pointers, the read pointer is really not incrementing because the memory's FIFO is empty. So it's like an error condition. It ignores this, right? Anything after. So there you have it, guys. This is a simple example of doing an SC single clock FIFO. And we could implement it fairly easily. In fact, if you give the right requirements to ChatGPT, it can generate this for you. And it's fairly easy to generate these FIFOs and build more complex designs. So I'm going to continue on this path and bring you more episodes in this series where you can see how we do bigger and more complex designs using MYHDL. And MYHDL is fairly powerful. Like I said, it has advantages. You can go in more detail and you can dig into each section of the user's guide that I was showing you earlier. Why MyHDL. So if you go through this section, most of the key things are described here. If you can go drill down into some of these, see how they work, that would be fantastic for you to start. And then obviously there's a section here on examples. So in docs, it's good to go through these examples. Obviously you could start here, something very simple like hello world, try something like flip-flops latches, Johnson's counters, and then the rest is up to you how far you want to go. But definitely it is an excellent tool, and I would highly recommend you starting with MyHDL in your free time. If you can try it out, get some of the designs going. All it needs, like I said, is Python, and you can easily install the GTK Wave and you are up and running. 2 simple things, no license, no price, completely free, and it is fantastic to do your modeling work. So that's it for this episode, guys. Again, I love MyHDL, can't say enough good words about it because it's free. It helps me do the modeling without any cost, and I love that. So with that, this is the end of the episode, guys. See you in another episode, and like, subscribe to my channel, and I'll see you some other time. Thanks very much. Take care and bye-bye.